Modern processors can execute billions of instructions every second, but that raw computational power is entirely dependent on a physical supply chain. If the processor cannot be fed data fast enough, it stops. This architectural limitation is named after the mathematician who first formalized the computing model we use today, the von Neumann bottleneck. In a sequentially executing computer, when a CPU requests a piece of data and it isn't immediately available, the processor has no choice but to idle. It sits frozen, wasting millions of potential calculation cycles waiting for a delivery. This logarithmic staircase chart outlines the actual latency scale of system memory, showing exactly how severe this data starvation can be. At the very top, closest to the processor, the internal L1 cache can retrieve data in about 1 nanosecond, but internal cache is extremely small. If the CPU must reach out to main memory or RAM, retrieval time drops to roughly 100 nanoseconds. If the data isn't in RAM, the system must access secondary storage. Reaching into a solid-state drive takes about 100,000 nanoseconds. And if the system is forced to pull data from a mechanical hard disk drive, the wait time stretches into the millions of nanoseconds. Accessing a mechanical hard drive takes 10 million times longer than accessing the processor's internal cache. Because of this massive disparity, high-performance computing design is an engineering battle dedicated almost entirely to hiding memory latency. That 10 million-fold delay is not a software bug. It is a strict limitation imposed by physical hardware mechanics. This 3D wireframe models the internal components of a traditional hard disk drive, which relies completely on moving physical parts to function. When data is requested, the mechanical actuator arm must physically swing across the disk to find the correct data track. This kinetic movement is called seek time. Once the arm is in position, the system experiences rotational latency. It must wait for the platter to physically spin until the correct sector aligns exactly beneath the read head. Because the drive relies on actual physical motion, its total access time is permanently trapped in the relatively slow millisecond scale. This abstract grid diagram represents NAND flash memory, the core technology inside solid-state drives. NAND flash bypasses kinetic limits by relying on electrical pathways instead of moving parts. The SSD controller reads data pages instantly through this electrical grid. There is no arm to move and no disk to spin, completely eliminating seek time and rotational latency. By replacing mechanical physics with electrical logic, solid-state drives cut access latency 100-fold. But even with microsecond response times, the bottleneck simply shifts from the drive's internal mechanics to the pathways connecting it to the CPU. To understand where the bottleneck goes next, we have to evaluate how data actually moves from these storage drives, across the motherboard system bus, and into the processor. This diagram models the system bus as a toll highway, with cars representing data packets. Latency is the total time it takes one single car to travel from the entrance gate to the exit gate. Bandwidth, on the other hand, is the absolute physical capacity of the road. It is determined purely by the number of lanes available to carry data side by side. But a wide road doesn't guarantee fast travel. Throughput measures the actual real-world rate of cars successfully exiting the highway per hour, accounting for traffic jams, processing delays, and system overhead. As shown in this equation, the relationship between these metrics is straightforward. Total transfer time equals the data size divided by the bandwidth, plus the latency. This equation reveals a structural problem. Engineers cannot solve the von Neumann bottleneck simply by increasing bandwidth. To truly optimize the system, they had to alter how the CPU manages the traffic itself. The central engineering problem engineers faced was synchronization. How do you program a processor operating in nanoseconds to communicate with a drive operating in microseconds without forcing the faster component to pause? This logical map illustrates the earliest and most primitive communication method, programmed I/O, commonly known as polling. In a polling system, the CPU repeatedly sends a signal to the disk, asking if the requested data is ready. This locks the CPU in a waiting loop, throwing away millions of valuable clock cycles on a simple status check. To free the processor from this constant checking, engineers developed a new architecture, interrupt-driven I/O. Instead of having the software repeatedly ask for updates, the burden of notification was shifted to a physical hardware trigger. Under this new workflow, the CPU issues a data request to the disk, and then immediately turns its attention to executing a completely different program. When the disk finally has the data ready, it rings a hardware bell. It sends an electrical interrupt signal across the bus to the CPU, telling it to pause its current work. But this system retained a severe flaw. Once interrupted, the CPU had to act as a manual courier, physically moving the requested data byte by byte from the disk and into the RAM. Interrupts successfully stopped the CPU from waiting, but forcing a high-speed processor to manually haul data still caused unacceptable bottlenecks. The definitive solution to the data courier problem required taking the CPU out of the transport business entirely. This was achieved through direct memory access, or DMA. This diagram details the addition of a DMA controller. It is an independent, highly specialized hardware chip whose only job is moving data across the system bus. In a modern protocol, the CPU delegates the transfer, telling the DMA controller the source, destination, and size. The DMA controller then seizes temporary control of the system bus to execute the transfer. Data streams directly from the storage drive into RAM, completely bypassing the CPU, which is now entirely free to continue processing other instructions. The elegance of this system is its efficiency. The DMA only interrupts the CPU exactly one time, when the entire multi-megabyte transfer is completely finished. Direct memory access decouples computation from data transfer. It allows modern processors to reach their maximum theoretical efficiency without being dragged down by storage latency. Yet, even with solid-state drives and direct memory access, physical constraints still exist. If a system ignores its hardware limits, the entire architecture collapses. This occurs when a computer becomes I/O-bound. It is a condition where a high-performance CPU is forced to sit completely idle because its data supply chain has dried up. This grid represents physical RAM. The most common trigger for an I/O-bound failure state happens when this memory reaches 100% capacity. To prevent an immediate crash, the operating system initiates an emergency failsafe known as paging or virtual memory. The OS carves out emergency space on the vastly slower secondary disk to act as overflow RAM, moving inactive data there to clear space for new operations. While virtual memory successfully keeps the computer from crashing, it introduces a critical vulnerability. It tightly links the speed of active RAM back to the agonizing latency of the storage drive. Relying too heavily on this virtual memory triggers the ultimate systemic failure, a condition known as thrashing. The failure begins when the CPU urgently requests a piece of data that the operating system just moved to the slow secondary disk. The OS must pull requested data into RAM, kicking another block out to the disk to make room. The system enters a continuous death loop, swapping data back and forth. The entire bus bandwidth is consumed by moving data. Actual computation drops to zero. This paralyzed state is defined as thrashing. The system is entirely overwhelmed by the overhead of data movement, leaving no resources to actually execute instructions. True high-performance computing cannot be achieved simply by increasing processor clock speeds. It demands a flawless architectural balance between storage physics, bus bandwidth, and intelligent I/O delegation.